This video is about the dynamics of pendulums, which really talks about the forces that are acting on the pendulum at some different spots of the pendulum's motion. So I have 5 different spots that are marked on the screen right now. We have the top point on the left that the pendulum will start at. Then we have another point down a little bit below there. We have the equilibrium position, then coming back up another 2 spots where the last one is the highest point that it reaches on the right hand side. So if you look at the overall path of these points, it is circular in nature, and it's important to understand that the pendulum does move in a fairly circular path because we can use our principles of circular motion when we're analyzing the dynamics, when we're looking at the forces that are acting on our pendulum. So I'm going to start out with the left-hand spot, so the very highest point that we're at on the left-hand side, and I'm just going to draw the 2 forces that we have. And the 2 forces that we have acting on it at this point are gravity, so we have a force of gravity going downwards, and we also have a force of tension. So the force of tension is going to be upwards. It's not perfectly drawn, but as we go through, I'll explain a few things. We also know that for this pendulum at this point, we have the pendulum with an angle of theta from the vertical, so I'll just mark that at the very top. One of the easiest things to do is, instead of trying to look at the forces on a standard x and y axis, it's easiest to set your axes, rotate your axes so that you have a tangential axis and you have a radial axis. So what that means is we have one axis that's just going to be set through basically through the free body diagram, but it's going to be in the same direction as that tensional force. So the tensional force is going to be on the one axis, and then the other axis is just going to be, that's going to be perpendicular, so that's going to be our tangential axis. So what we're going to do now is, instead of splitting up the tensional force into components, now we can split the gravitational force up into components. So if we look at what we have here, we have one component there of gravity, then we have another component that's going kind of downwards due to gravity, and this forms a right triangle. Now what happens is, if you look at the geometry involved, we have the angle theta at the very top. So if I were to create a right triangle, essentially I'd have a few different options of creating my right triangle, and I could create triangle after triangle after triangle, and angle after angle after angle, and what ends up happening is that this bottom angle ends up being theta. So the bottom angle inside this right triangle that we have set up with our gravitational force vectors is going to be that angle theta. So in this case, what ends up happening is that this component that we have kind of in the x direction, that tangential direction, is going to be the force of gravity times the sine of theta. And that's important to understand. The other component that we're going to have, this y component, as I'll call it, force of gravity, that's equal to tension in this case. And this is what I mean. It's not drawn perfectly to scale. The force of tension should have the same length as the force of gravity. The reason why the force of tension and the force of gravity are equal is because, since we're talking about a circular path, the tensional force is a radial force. The force of gravity is kind of the opposite direction as the radial force, but there's no velocity at this point. The pendulum is not moving at the top point. Since the pendulum is not moving at the top point, it means that your centripetal force is 0, because we know centripetal force is mv squared over r. So mv squared over r is going to equal 0 since velocity is equal to 0. So that means we have no net radial force. So that means that that gravitational force and that tensional force are going to be completely balanced. So that means that we have only one force, one net force that's acting on the pendulum, and that's this force of gravity. So that Fg sine of theta, that component of gravity, is our net force that we have acting on our pendulum. It also means that we have an acceleration here. So this is a tangential acceleration in the same direction as this tangential force that we have. So that's important to understand at that point. If we move on to the next point, so if we move on to this point right here, we have a force of gravity that's downward still. The force of gravity is going to be the same. The magnitude of the force of gravity is going to be the same at this point as it was at the top point because the mass is still the same of the pendulum. The tensional force, though, is a little bit greater here than it was. I know it doesn't look the same, but it's a little bit greater, and the reason why is because the pendulum is moving at this point. Because it's in motion, we do have a centripetal force, since we do have a velocity. Since we have a centripetal force, we have to have a net force that's inward towards the center of the circle. So we must have a greater force of tension than we would have if I just split this up into the components. We must have a greater force of tension than we would have this y component due to gravity to keep the pendulum moving in that circular path. So it's important to understand that when we're looking at our pendulum, that tensional force isn't remaining constant. That tensional force is changing, and it's changing as the pendulum is in motion. So what's going to happen in this case? Because that is changing, we're going to have our two different components. We're going to have a component that is tangential, so we have a tangential force, which is still Fg times the sine of theta, except in this case, theta is less. And then we also have a radial force. So we have a radial force, and that's just the net force, the difference between the tensional force and this y component of gravity that we have there. I don't care too much about the radial force. All the radial force means is that we have an inward force, a net inward force, so we're going to have a radial acceleration as well. What's more interesting is the fact that we have this tangential force. So we still have a tangential acceleration. But what's different in this case from before, and this is another important point to understand, is that since it's still the force of gravity times the sine of theta, that's going to be this tangential force that we have here, and theta is decreasing, it means that the tangential force is going to be lower in magnitude at this point. So we had a greater magnitude tangential force at the top. We have a lower magnitude tangential force at this point. That means that the tangential acceleration will also be lower at that point. So that's another very, very important point to understand. As we move on to our next point then, at the very bottom, this is the equilibrium point. At the equilibrium point, what we have is the greatest tensional force that we have throughout the entire motion. We have the same force of gravity that's down. So we know we have a net force. We know we have a net force that is upwards. So a radial net force that is upwards, that's going to keep it in the circular path. Because the forces are up and down, we're going to have zero tangential force. So at this equilibrium point, we have zero tangential force, which means we have zero tangential acceleration. So tangential force here is 0 newtons. That means that our tangential acceleration is 0 meters per second squared. So that's another important point to consider. If I were to keep going on, what would happen is I would end up having a tangential force that's down and inwards over here. I would have another tangential force that's down and inwards over here, where the magnitude of this last force would be greater than the magnitude of the previous force. So the direction is changing for our tangential force. The magnitude of the tangential force is changing, the direction of the tangential force is changing. So that's another key concept when we're looking at our pendulums. That means that this isn't uniform circular motion when we're looking at our pendulum, because we don't have a constant force, we don't have a constant acceleration. So you really have to understand what's going on here. One of the most important things I want you to see is that that tangential force that we have is always caused by gravity. So the tangential force is caused by gravity. So everywhere we're at here. So gravity is that tangential force. It's a little bit of a different component in each one, but it's still a component of our force of gravity everywhere. Since the tangential force is always pointing towards the equilibrium point, that's the other thing that you need to understand. We call this a restoring force. So that force of gravity, which is our tangential force is called a restoring force. The reason it's called a restoring force is because this force is trying to push the pendulum back towards this equilibrium position. So whether you're on the left-hand side or you're on the right-hand side, this tangential force is pushing the pendulum back towards equilibrium. So it's called a restoring force. So that's what's really important to understand, that you have this restoring force, this force of tension. We have tangential forces, we have tangential accelerations, we also have radial forces, and the radial forces exist not everywhere, just like the tangential forces don't exist everywhere. So wherever possible, just draw out your free body diagram at whatever spot you have, and then try to understand, try to figure out whether you have a net radial force or whether you have a net tangential force, and that's going to help you understand what's going on with the dynamics of the pendulum.